Hi, welcome to Sunil Maths tutorial, functional analysis class number 60. In this video, we learn definition of projections on a Hilbert space and then a theorem depends upon the projections. Let us see the projections on a Hilbert space. Before going to learn the projections on a Hilbert space, let us see the projections defined on a Banach space. Suppose capital B is a Banach space. Suppose capital B is a Banach space and P maps capital B into B, P maps capital B into B, P maps capital B into B is a continuous linear transformation. Capital B is a Banach space. P maps B to B is a continuous linear transformation. Then P is a projection. P is a projection on capital B. P is called a projection on capital B if and only if it is idempotent operator. It is known as idempotent operator on capital B. Idempotent means P square is equals to P. P square is equals to P. So, an idempotent operator is known as a projection on a Banach space capital B, where this projection or this operator defined from B to B and which is continuous as well as linear transformation. It is a continuous and linear transformation from B to capital B. Here, you can define capital M is equals to the set of all those elements Px such that x belongs to capital B. This is known as range of projection P, and capital N is equals to set of all elements x belongs to capital B such that Px is equals to 0. This is known as null space. Of the projection P. Though these two are again very important. Range and null space. M is equals to range, the set of all elements Px such that x belongs to B, and N is equals to x belongs to B such that Px is equals to 0 is called null space of the projection P on capital B, on the Banach space B. It is very clear both M and N are closed subspaces. Both M and N are closed subspaces of the Banach space capital B and also satisfies the condition capital B is equals to M direct sum N. It means the Banach space capital B can be written as the direct sum of the range and null space. Further, you remember here an element x belongs to capital M means or implies and implied by Px is equals to x. Because P is a projection. And M is the range of the projection. It means this condition means P consists of exactly those elements. P consists of exactly those elements in capital B which are left unchanged by P. Unchanged by P. The meaning of Px is equals to x means P consists of those elements from the Banach space capital B which are left unchanged by P. And also further, since B can be written as direct sum of M plus N, an element Z belongs to capital B can be written as Z is equals to X plus Y. Where this X belongs to capital M and Y belongs to capital N. Also, Pz is equals to P of X plus Y. You can write this Px plus Py. Here, this y belongs to capital N and N is the null space. Then Py is equals to 0. So, you simply get Px. And where again x belongs to capital M, by the definition of M is the range. So, Px is equals to x. You observe that Pz is equals to x. That's it. So now, in view of these projections defined over the Banach space, we define a projection on Hilbert space like this. A projection, a projection P on a Hilbert space capital H is said to be is said to be is said to be a perpendicular projection, a perpendicular projection, a perpendicular projection on capital H if the range capital M, the range capital M and the null space capital N of capital P are orthogonal, that's it. Okay, we learn some additional properties of this projection. First we prove a theorem and then we go for some exact properties or exact definition of the projection or perpendicular projection on a Hilbert space. Let us see the statement. If capital P is a projection, one of the important theorem, if P is a projection defined on a Hilbert space capital H with range capital M and null space capital N, okay, then M is perpendicular to N implies and implied by P is self-adjoint, and in this case N is equals to M orthogonal. N is equals to M orthogonal. Let us prove this statement step by step. Let capital H be a Hilbert space and P is a projection. P is a projection defined on capital H. P is a projection defined on capital H. By the definition of projection, P square is equals to P. By the definition of projection, by the definition of projection, P square is equals to P, and P is a mapping or linear transformation which is continuous from H into itself. Now let us take capital M be the range, and capital N be the null space of capital P on capital H. Also by definition of projection, H can be written as a direct sum of M and N. Now we shall prove that. We have to prove that M perpendicular to N implies and implied by P is self-adjoint as well as P is self-adjoint, and in this case this N is equals to M orthogonal. So let us prove this. Right, now take an element Z belongs to H. Let Z belongs to capital H, and this H is direct sum of M and N. So this Z can be written as sum of two elements X plus Y, where X belongs to capital M and Y belongs to capital N. Now calculate the inner product Pz comma Z. It is equals to Pz comma Z P x plus y comma x plus y. So you simply write px plus py comma x plus y. Again you can write px this py, because You see here already in the introduction part, n is null space. So py is equals to 0. X belongs to m, it means px is equals to x by definition of null space and range. So here px becomes, here this px becomes simply x and py becomes 0. Here x plus y, x comma x plus y. So this can be written as again inner product of x comma x, inner product of x comma x plus inner product of x comma y. Again you see here inner product of x comma x, inner product of x comma y. Here x belongs to capital M and y belongs to capital N and m is perpendicular to n, which implies as inner product of x comma y is equals to 0. It means this term completely equivalent to 0. We simply get x comma x. X comma x. Therefore, what we show that inner product of pz comma z is equals to inner product of x comma x. Inner product of x comma x. Now, let us calculate in a similar manner p star z comma z, which is equals to z comma pz, z comma pz. It is equals to z comma x. It is equals to x plus y comma x. It is equals to inner product of x comma x plus inner product of y comma x. Again this is simple calculation, you get again x comma x because this term becomes 0. Now what we show that p star z comma z also equivalent to x comma x. pz comma z is equals to x comma x. P star z comma z is equals to x comma x. From these two conditions we conclude that inner product of pz comma z is equals to inner product of p star z comma z. So this condition shows as p minus p star into z comma z is equals to 0 for all z belongs to capital H, which implies p minus p star is equals to 0, which implies p is equals to p star. P is equals to p star. If p is equals to p star, then what we say that p is self-adjoint. P is self-adjoint. So we assume that m is perpendicular to n. We take this m is perpendicular to n. We prove that p is self-adjoint. P is self-adjoint. Now let us try to prove the converse part. In this part, let us assume that P is, we prove the converse. We shall assume that, suppose P is self-adjoint. And we have to prove that M is perpendicular to N. So right, to prove this, let us take x be any vector. Let us take x be any vector in capital M and y be any vector in capital N. Then it is very obvious, because P is a projection, Px is equals to x. Because P is a projection, Px is equals to x. And by our assumption, P star is equals to P. And also by the definition of null space, Py is equals to 0. These are the properties. So you can write the inner product of x comma y as Px comma y. Which is equals to again x comma P star y. Which is equals to this x comma P star is equals to Py. So this is equals to x comma 0. It means inner product is 0. Inner product is 0 means inner product of x comma y is equals to 0 means x is perpendicular to y. We take the element x belongs to capital M and we take the element y belongs to capital N. We show that x is perpendicular to y. This is true for every pair. Therefore, we conclude that M is perpendicular to N. Therefore, M is perpendicular to capital N. So, we assume that P is self-adjoint. We prove that M is perpendicular to N. So, our theorem is almost completed. Now, it remaining to prove that. It is remaining to prove that N is equals to M perpendicular. So, right, let us take, to prove this, let us take the element x belongs to capital N. If x belongs to capital N, if x belongs to capital N, by the definition of null space, by the definition of null space and our previous theorem, this x is perpendicular to capital M. This x is perpendicular to capital M means this x belongs to M perpendicular. M perpendicular. It means we show that x belongs to capital N implies as x belongs to M perpendicular. It means this N is subset to M perpendicular. N is subset to M perpendicular. Now we have to show that the opposite side. Okay, suppose let us assume one condition. Suppose capital N is proper subset of M perpendicular. If capital N is proper subset of M perpendicular, then N is proper closed linear subspace of the Hilbert space M perpendicular. Therefore, by previous theorem, there exists a non-zero vector Z0 in M perpendicular such that Z0 is perpendicular to capital N. Z0 is perpendicular to capital N. Right. Since Z0 perpendicular to M perpendicular implies as Z0 is perpendicular to M. Z0 is perpendicular to capital M means, and also we have here Z0 is perpendicular to capital N. Z0 is perpendicular to capital N. It means Z0 is perpendicular to H, because Z0 is perpendicular to M, Z0 is perpendicular to N, therefore Z0 is perpendicular to H. Z0 is perpendicular to H means H is a Hilbert space, this Z0 is equals to 0. But what is actually there? Z0 is there exists a non-zero vector Z0. There exists a non-zero vector Z0. So this is a contradiction. This contradicts the fact that Z0 is a non-zero vector. Z0 is a non-zero vector. Therefore, we conclude that capital N cannot be a proper subset of M perpendicular. Therefore, we must have N is equals to M perpendicular. This is very important property of the projections. So here you observe the statement of the theorem which we prove here. If P is a projection on a Hilbert space H with range M and a null space N, then M perpendicular to N implies and implied by P is self-adjoint, and also N is equals to M perpendicular. By all this theory discussed here, we conclude like this. An operator P on a Hilbert space capital H is a projection if and only if it satisfies two conditions. The first one is P square is equals to P, as well as it is self-adjoint P star is equals to P. So by had this definition. An operator P on a Hilbert space H is a projection if and only if it is simply idempotent as well as self-adjoint. This condition shows as idempotent and this condition shows as self-adjoint. That's it. And remember that zero operator and identity operator are projections on capital H. That's it. Keep learning. In the next video, we learn one more theorem depends upon the same projection definition. Keep learning.